So I'm going to be teaching YouTuber Melissa Lucy electron configuration today. And it's going to help her stress less, and it's going to help you stress less. So breathe, we're going to get through this together. So just starting off with like what orbitals are and what they represent. This is like a fancy definition of saying like, oh, it's the probability of finding an electron at a point in space. I just want you to think that electrons hang out there, okay? Electrons like to be in orbitals. That's probably the most likely place that we could find them. I can't say that it's definite, but we know that electrons exist within orbitals. Now, there are different types of atomic orbitals that you're going to see, specifically like different shapes. So the first one you're going to talk about is known as S, and that's like more of a sphere shape. So S is going to be our sublevel. This is going to be really important to understand like, oh, what's a sublevel? What's an orbital? And then how many electrons are in there? Because I've actually seen this question all the time, just asking like, oh, how many orbitals are possible in a P subshell? And like that little, terminology, if you don't know it, it's going to be difficult to answer.
Okay.
So just knowing, okay, it's an S subshell, and then there's only one orbital that can hold 2 electrons. So by one orbital, you're either going to see it kind of represented like this, as an orbital diagram, where it's kind of like boxes, or you might just see it as a line. So you might see it like either like this, where it says 1s, and then you might also see it as just like a line, and it says 1s, and then we would actually draw electrons. Just to note that electrons spin in opposite directions when they are actually in the same orbital. So this should all kind of sound familiar.
Yes.
Okay, cool. So the next subshell that we have is the P subshell that has 3 orbitals, and that can hold up to 6 electrons because there are 2 electrons per every orbital. And since, 3 times 2 gives us 6, that's where the 6 electrons come from. So I did put the shapes. I don't expect you to know the shapes, all these like kind of funky shapes. I don't expect you to know that, but it's just a good visual. This is actually what we kind of think it looks like. And let's move on to the next one. D subshell has 5 orbitals and can hold 10 electrons. And then lastly, F subshell has 7 orbitals and that can hold 14 electrons. This is probably the rarest one that you'll see. Typically, they don't have you draw an orbital diagram for like an F subshell because it's so large. But just in case, we'll do one.
Okay.
You never know. And then something to also note is just how the orbitals are going to fill. So it's going to fill the lower energy orbitals like this 1s, and then it goes to 2s, 2p, 3s, and so on until it goes to like the higher energy orbitals. So always fill the lower first, and then it goes to the higher. And how you know what's low, what's high, like if you're not even looking at this chart, is just based on the coefficient in front. So like since this is 1, that's lower than 2, so that's how you know, okay, I'm going to fill that first.
Okay, and the order is according to the letter also?
Yes, so we'll go over that.
Okay.
We'll definitely go over the order, and then I'll teach you. I don't want you to memorize the order because I think that is like, 1, it's terrible to have to memorize. And 2, it's going to be a lot easier to just know where everything is positioned on your periodic table. And then from there, you'll be able to do it. So it's going to be a lot of counting. Like it's going to seem kind of tedious. But once you learn how to actually use the periodic table to find everything, you don't have to remember the order.
Okay.
Or memorize the order, I'll say. So just knowing that these first 2 groups are our S subshell. And then same thing here with helium. This actually would have been helium. And then next for our P subshells, that's going to be in that purple area. And then D is going to be that transition metals. And then lastly, this last part is going to be F. So we will do an example of every single type, meaning like, one in the S, one in the P, D, and F. Before I move on, something that's going to be really important specifically with D and F is just the order of it. So this is going to say, you're probably going to either see this as n-1 or n-2. Before I even get to that, I just want you to know that n is talking about that coefficient in front. So N is talking about like the energy, as we saw before, you know, where like 1s is going to be lower energy than like 2s2. So this is what's represented by N. So N can be 1, 2, any sort of integer that we have. So by N minus 1, that just means it's going to be 1 less than the row that it's in. So like this would have been, you know, row 1, row 2, 3, and 4. So this would have been like, instead of like, actually, where is iron? Actually, let's say titanium. So let's say if we're ending at titanium, instead of this being 4D, because it's in that level, because it's on D, and that's always N minus 1, that's actually going to be 3D. Kind of making sense. We'll go over a bunch, but for now, I just want you to understand the D is always 1 less than the row that it's in. Like it's in row 4, but that N is actually going to be 1 less, so 3.
Okay, but the S section will always be just what it is.
Correct. Same with the P.
Okay. I think I get that.
Cool. We'll go over it, don't worry. But
okay.
The next one is also F. That's actually 2 less, so it's N minus 2. So that's 2 less than the row that it's in. And then beware of this for the F. Let me see if I can, I'll get to it. But we'll cover that in a second. But for now, I just want you to know that little bit of, okay, D, that's not going to be the same as the row it's in. It's always going to be 1 less. And then F, it's always going to be 2 less than the row that it's actually in. But S and P stay the same.
Okay.
All right. So just understanding what everything represents in our electron configuration, knowing that they're basically just telling us how electrons are occupying our orbitals, and specifically, you know, what energy level they're at or what type of subshell they're at. So sure, this is the order. And like I said, I think it would just be a pain to have to remember all of this, you know, so it's going to be a lot easier to just know where everything is on the periodic table and go from there.
Yeah.
So another thing to also know, as we mentioned, was just like what everything means for our electron configuration notation. So like this is actually going to mean that it's the orbital. And then that superscript is going to be the number of electrons that are in that orbital.
So is the orbital the position of it?
So it's pretty much like where, here, let me go back to the different types. Like, let's say for like S, like we can imagine that it looks like this, like kind of like a sphere. It's telling you what type of orbital it's going to be in. So like whether it's going to be an S, P, D, or F. Like that's kind of what it's talking about.
Okay.
And then typically, you know, based on like S, P, D, and F, it's also going to help us understand, you know, either the shape of the orbital. Actually, that's what that tells us. That tells us the shape. And then that coefficient in front tells us how high that is on this like energy table. So how much energy that orbital has, or that atom has, I should say.
Okay.
Starting to kind of make sense.
Yeah,
I know there's like little things that you always have to know everything about.
Yeah.
Okay. So I wanted to practice a bunch with this because it can get a little bit tricky. So let's just start off with doing several different types of, I'm going to call this as like the full electron configuration, because there is, they call it either an abbreviated, noble gas method, condensed, shorthand, there's so many words, but typically they call it a condensed electron configuration. And it's kind of like just a way that we can abbreviate it. So instead of writing like the whole entire thing, let's say if it was all the way at the bottom, that would be way too long.
Okay.
And you'll get what I mean in a second. So if I were to start off with just writing the full electron configuration for, let's say, hydrogen. So I'd see, okay, well, this is the first row. And I know that that's in the S location. So that is 1. So I'm getting that 1 from the row it's in. And then I know, okay, well, this is S because it's telling me right here. So S. And then next is, it's also going to let me know, let's see, let me do a different color, purple, how many electrons hydrogen has. And then we know, okay, everything's neutral right now. So it's going to be the same amount of electrons as our atomic number. which is that 1. So 1.
Okay.
Do we see that?
Yes. Yeah. So that means that's the only one, like, for hydrogen?
Yes, but it's going to change when we have more electrons. So, and it's also going to be really important to just know, well, S can only have 2 electrons. Like, that's it. That's its max. And then P, its max is going to be 6. And then after that, D is 10. And then F is 14. We can't go past that number.
So once you do, then you go into the next group.
Exactly.
Okay.
Yeah. So here, I'll erase that for now. So let's say if I were to do beryllium, then I'm going to look again here and I'm going to see, okay, I have to start in the very, very beginning and then make my way all the way to beryllium. So I'm going to start off with 1. So 1. And then this is S. So I'm going to say 1s1, 1s2, because I'm literally going across, and then I'm going to come back around to beryllium. So then this is 1s2. Good so far. Is that making sense? I can say it again.
So, but I'm saying, so you don't count like each individual one, so you're not like saying like 1s1 for hydrogen and then
another 1s1? Yeah.
So you go all the way to the end of that group and then write it, or?
Yes, and the reason is because it's past that point. So it's kind of like we have to go all the way until we get to the element that we're looking for. And because this is 1s1 and this is another electron in the same row and in the same orbital or sublevel, then I know that this is going to be a 2. So it's accounting for that because this is 1s2. Because this is 1s1, this is 1s2.
Okay, then what about the lithium?
So then because we passed lithium, like beryllium is past lithium, then I know that this is going to be, well, 1, this is at 2 because it's the second row, 2s, and it's like I'm counting, 2s, 1, 2.
Okay.
Okay, cool. And then if I were to do, let's look at carbon. Why not? So we'll do the same thing for carbon. So I'll start off in the very beginning. So this is 1s, 1s1, 1s2. I'll do a different color.
So anything past helium, we're always going to start with 1s2.
Yes, correct.
Okay.
And it's like anything past kind of like the next point, you're going to fill the orbitals entirely. Okay. So the same thing here, because we're going to carbon, I'm passing this point, right? This is 2s, 1, and 2. And then I'm going to keep going straight across until I get to carbon. So this is still in the second row, but now we've changed the sublevel to P. So now it's P, and then I'm going to count again, 1 and 2. So 2p2.
Is P still like n equals, like, you know,
do we remember that it is? Yes.
Okay.
Yeah, it's still going to be the same number as the row it's in. It's only D and F that change.
Got it. Okay.
So another thing to also note is just if we were to count the electrons, like the superscripts here, which is the electrons, that would give us the same amount of electrons as beryllium or whatever element we're looking for. So like here, this is, 2 plus 2 gives us 4. Beryllium has 4 electrons. And then same thing here for carbon. So 2, 4, 6. Carbon has 6 electrons. So you might get a question where they actually give you the electron configuration and they ask you to say, to figure out what element it is. And that's a trick. Just add everything up and that'll give you the correct amount of electrons.
Okay, got it. And then you would just find it on the periodic table.
Yes.
Okay.
Yeah. All right. This okay? I'm going to do another one.
Yeah, this is good. This is good practice. I was very confused, so it's nice to know that there's a system and I don't have to remember all of those because that's really a lot.
Yeah. Like there's no need to memorize it. Once you understand it, that's all that matters. I'll do maybe one more because I do want to talk about something else. let's see. Okay. Let's do phosphorus. All right, so you want to try?
Sure.
No, but sure.
Okay, so 1s2 for sure. So we're passing helium.
Cool.
And then 2s2.
Correct. Good, good. Going straight across. And this I just want you to count. So what row are we in currently?
We're going to P now.
Right, and then what row? Like,
2.
Okay.
Oh, so we just do 2. P.
Yeah.
Okay.
and then count. So we're going all the way to, like, this is what we're trying to get, phosphorus.
Okay.
We're going to have to keep going all the way through. So we can literally just count. So 1, 2, 3, 4, 5, 6, which tells us, I know that for the P subshell, only 6 electrons can be there. Like, that's the maximum. Good. Keep going. I'm going to turn around.
Okay, so now it's going to be 3s2.
Go straight across.
This is so weird. I've never done anything like this. Okay. It's like, okay, so now we are going to do 3p3.
Yes.
Okay.
Cool. Okay, good. So that's the general idea of this. It's going to change a little bit, of course. There will be exceptions, but knowing, like, having a good foundation of this, understanding what it should be, is going to help a lot. So the other thing I wanted to talk about, like, this is the full electron configuration. Now we're going to do the condensed electron configuration. So the condensed electron configuration is going to look something like this. So let's do this for phosphorus. Here. What you're going to always do, like the notation of this, is you're always going to put whatever noble gas is in the row right above it, right above the element that you're looking for. So that noble gas is going to go in brackets, and then the remaining electron configuration, or, like, subshells, are going to go at the end. So if I were to look at phosphorus right here, what's the noble gas that is right before it? Like, in the row right before it.
I don't know what the noble gases are.
This row. Okay.
Oh.
Or sorry, this group, not row.
Okay. So
These are the noble gases.
got it.
All of these, yeah.
Something Ne, I just don't know what that one means.
Neon, yeah.
Oh, that's neon. Okay, got it. Still working on that.
So neon would basically take the place of all of this. Like, all of this gets replaced with just the noble gas. And we know that because if I were to do the electron configuration of neon, I would start with, okay, well, 1s2, make my way. I'm here. Now I'm at 2s2, go straight on across. And then I'd end at 1, 2, 3, 4, 5, and 6 at 2p6. So do we see how that literally replaces this chunk, like this beginning portion of our full electron configuration? And, like, now it's like neon telling us, oh, this is kind of like a bookmark, like kind of like a placeholder to tell you where to start and then where to continue.
Yeah, and it adds up to 10 too, right? So
Right.
okay.
So then from there, I can just put the remaining part of it. So the remaining portion of this would have been 3s2, 3p3. So this is the condensed electron configuration.
Okay.
The top part.
That top part is the full electron configuration.
Yeah, that's nice.
Okay. Cool. We'll do more. So let's do nitrogen together. Why don't you start it off?
Okay, just the regular one?
Just the regular one.
Okay. So nitrogen is right there, yeah. So we do 1s2.
Good.
Here.
2s2.
Good. Going straight across.
2p3.
Perfect. So now let's try doing the condensed electron configuration.
Okay, so helium is right there. So we just put He in the brackets.
Perfect.
And then it's going to be... Oh, I still have to do... Okay, so...
What's the remaining part? Yeah.
2s2. 2p3.
That's it.
Okay.
Yeah, not too bad.
Yeah.
Perfect. Now let's do something that is in that D subshell. So we'll do this one together. I'll look for wherever iron is, which is right here. So I'll start off with just the typical one, the full electron configuration. So starting off with, actually, I'll have you start off, and then once we get to the D level, I'll explain what to do.
Okay. So 1s2. 2s2.
Good.
2p6.
You're right.
Okay. 3s2.
Correct.
And
We're
then
moving across.
3p6.
Perfect. Going around again.
And 4s2.
Good. And then once we get to that D sublevel, we know it's always going to be one less than the row it's actually in. So instead of 4D, it's going to be 3D. And then you count to wherever your element is. So from here, it would have been 1, 2, 3, 4, 5, and 6.
So 3d6. Okay.
Yeah. So always one less. The D is always like n minus 1, one less than the row that it's actually in. So instead of 4, it's 3.
Got it.
What would the condensed electron configuration be here?
It would be... Is that argon?
Yes.
Okay. So Ar... 4s2.
Good.
And then 3d6.
Perfect. That's it. Yeah, that's it. Awesome. We'll do some more. All right, so this one's going to be a little bit longer. We're going to go to PR, which is all the way down here.
Oh my gosh.
Yeah.
I'm going to have you walk me through it until we get to here, and then I'll explain.
Jeez, are we gonna have space?
We'll have space. I'll have to write it a little bit smaller, but we'll have space. So let's just start off with the first one. Go ahead.
Okay. 1s2. 2s2.
Good. Yeah.
2p6.
Good.
3s2. 3p6.
Great.
4s2.
Now what's this next place?
Since we're not stopping anywhere, do I still have to do the whole thing where it's less?
You do. And it's because you have to go through the entire periodic table until you get the element that you're looking for. And that's all the way down here. Yeah.
So we're going to still be in the threes then?
Yes.
Okay. So I don't know how many's in this one.
10.
Oh, okay. Thanks. Okay.
Yeah.
So
The D always has 10 D sublevels, and then F has 14.
okay. So 3D 10. Okay.
Cool.
4p6.
You're right. Good.
And then 5 S2.
Good.
And then we're gonna do 4 this time.
Yeah.
Okay.
Perfect.
So 4d10.
Good.
Then we go back to normal. My poor brain right now. All right. This is like a puzzle. It's like a trick question to me. Okay. So now we're on 5. So 5p6.
Good.
And then 6s2.
Cool. And I'm going to say let's stop. And the reason we're going to stop here is because this group, like this, is actually meant to be like right here. And why did we do it this way? It has to do with properties, but unfortunately, that's how the periodic table is designed. So a clue here is just looking at the atomic numbers. So like seeing that this went from 56 to 71, that's not the right counting, you know, so from 56 to 57, that should make more sense. So then that's why we have to like stop here. So we're stopping like right here, and then we're actually going to go through this entire like level and then go back since this is 71.
Oh, okay.
So then this is our F block. So we know, okay, well, this is F, and this is always 2 less than the row that it's in. So we previously said we were in row 6. So what should that be now?
So it's going to be 4f3.
So yes, perfect. That's it.
Okay, so you just like, so I need to remember that point on the periodic table to know when the other ones come in.
Correct.
Okay.
Yeah, and we'll do several examples. What would the condensed electron configuration be here?
Do I still go based on where it would be, like right there?
Correct.
Oh,
Correct.
okay. So then, XE.
Good. Xenon.
Okay. So we start with 6s2
Good.
and then 5d10.
Hold on. It's still, we had that little break.
Oh, just kidding. Okay, I already forgot. And then we're going 2 minus, so 4f3. Oh, that's it.
That's it. Right, that's it.
I prefer that one.
Think of it.
Same. So once again, remember that xenon is taking the place of all of this.
Okay.
And then that's why we can just see, oh, okay, it just left the last little portion.
Got it.
Cool. Let's do another one. So let's do mercury, which is, let me put this in a different color, which is here. All right, so I'll have you start it off again. I am going to need more room. Let me delete this. Okay, go for it.
Okay, so 1s2,
Mm-hmm.
2s2,
Good.
2p6,
Perfect.
3s2, 3p6,
Good.
4s2,
Keep going.
and 3d10,
Good.
4p6,
Mm-hmm.
5s2,
Yep.
4d10,
Good.
5p6,
Good.
6s2,
Good. And breaking point. Right, because we're trying to get to mercury, which is 80, but we have to go through this entire...
Oh my gosh. Okay. I see what you did there. Okay. So now we're going to be at 4 again. So we do, oh wait, there's 14 in this one, right?
Yes.
Okay, so it's going to be 4f14
Good.
and then 5f14.
And then hold on. Then we go back. So this is 71. We go back to 70. Sorry, this is 70. And then we go back to 71. So now we're back in the D sub-level.
Oh, okay. Wow. So you gotta pay attention. Okay.
Yeah, definitely.
So now we're gonna be 5D 10.
Yeah, and that's it.
Oh my gosh. Okay.
Okay. And then, all right, I think we're good with that. Any questions so far?
No, this is like finally making a little bit of sense, which is nice.
Awesome. If you're enjoying studying along with us so far, make sure to give this video a like and turn on your notification bell because we're going to keep studying all semester long. All right, if you're ready to learn something new, click on the next video.